Welcome back to ECE 442-542. Sounds like everyone had a good weekend and you're still awake at this time of day. I never know whether it's going to be an early morning class that you prefer or a late or an early evening class, but we'll make this work. Some announcements before we move on to what we're going to talk about. Your passport is due on Sunday evening coming up. Homework number 1 is due in 2 weeks on the 28th. That's going to be here before we know it. There's plenty of material to keep you engaged on the website. There's review material if you want to review. There's readings. For whatever reason, did everyone get my email about the Shams outline? Now it's not even available. I don't know if you've tried that. So I'll see what I can come up with. I'll try to learn what the librarians are up to, but right now it's been removed from the library system, that particular Shams outline. So we'll stay tuned for that. I hope that you are aware that the contents is the section of D2L where most of the action is occurring this semester. The notes will be posted there, as will the video content, which means really the notes plus my audio. If you want to hear that, I guess if you're at home, you have no choice. Resources that you will be wanting to take advantage of is the notes that are provided under Discrete Time System Foundations. Chapter 1 and Chapter 2, you'll be wanting to read that prior to homework number 1, and Chapter 3 is probably going to be also necessary prior to exam number 1. And exam number 1 will be after homework assignments 1 and 2. Today what I want to do is have some show and tell. I'll give you a picture. If you haven't ever looked at the back wall in ECE 530 in the conference room, it contains an analog computer. If somebody now starts talking to you about an analog computer, you'll at least know what that's supposed to look like. And if you didn't make the connection yet, hopefully you will after today's class, the connection with integrators that you can build from components, from op amps, resistors, and capacitors, and these all-integrator block diagrams that we sketch in class. So if you wanted to say, how would I create an integrator with some circuits, let's just remind ourselves what that looks like. Then we will review and complete this transformation from the time domain into the frequency domain, and in particular, taking a state space representation in continuous time, we have first order derivatives, into a transfer function formulation. We'll just wrap that up, and then we will get into new material, which is difference equations. This is discrete time class. You want to be comfortable playing with differential equations, continuous time, transfer functions, but we also need to learn about difference equations, and one trivial maybe example is a linear difference equation first order that we can create based on a student loan. I know that will make everyone happy, but we'll talk about a student loan and see if we can now make the connection between that and linear difference equations, which are the dynamic domain that we will be living in this class, whether directly or indirectly by sampling a continuous time system. And then we'll start looking at how do we solve those. So instead of a differential equations class, the next 2 lectures here will be a difference equation class. How do we solve these linear difference equations when we don't have a forcing function, which is the homogeneous case, and when we do have a forcing function, which is the non-homogeneous. And then we'll get into block diagrams for discrete time systems. Instead of having integrator blocks, now we'll simply have a hold operation or a memory or basically a desk drawer where you put a value in and then one sample period later you pull it out. It's really a memory location, but it's an all delay block diagram, and we can start thinking about block diagrams in that form as well as the all-integrator block diagrams. As I said, we'll start today on a lighter note with show and tell. How many of you have actually seen this picture in ECE 530? Oh, well, good. I didn't know how many people actually look at the walls, but I guess the lectures are that exciting that you turn around and look at the back wall in 530. But that's where this is located, and you can see this piece of machinery, this hardware. That's the analog computer, or what they're calling an analog simulator, and they're connecting different points, but those connections now involve gains. You now have an integrator block, and you have summing junctions, and you can create these all-integrator block diagrams, and that's one way to solve differential equations, like we talked about last time. You can inject some generic input waveform, and out at the other side of that all-integrator block diagram will be the solution to that differential equation, that set of first-order coupled differential equations. And how do you build an op-amp? Right? I'm sorry, how do you build an op-amp? We're not going to go that far. How do you build an integrator? We're going to build an integrator assuming we have an op-amp. Here's an op-amp in a configuration that's fairly basic, just two passive elements, a resistor and a capacitor. The capacitor is in the feedback path, the resistor is in the forward path, and we simply inject a signal at the input terminals labeled V sub I, and we measure the output V sub O. This is now an ideal circuit, but it's now giving us an integrator, and we can convince ourselves of that by looking at it more generically. And I might say that the impedance in the input path I'll label as Z sub I. In our case, that's just R. And the impedance in the feedback path is Z sub F. And we can now do our circuit analysis by simply saying, oh, what's the current into A in all of these possible paths? What's the current, horizontal current going from right to left going into A? Or what's the current going into the op-amp, into the inverting terminal of that op-amp? This is an ideal scenario. It's 0. So we're not worrying about that particular horizontal current, which is, you could view it as the, well, it's not even in my formula or in my expression on the right of that schematic. But the current going from the input voltage source, V sub I, into A, is now V sub I over Z sub I, since we essentially have a ground, since there's no voltage drop across the inverting and non-inverting terminals of the op-amp, and the non-inverting input is in fact grounded, so that now V sub I is superimposed completely across Z sub I. The current then is V sub I over Z sub I. The one vertically coming down is now similarly V sub O is all dropped across Z sub F. We're summing those up. We solve for V sub O over V sub I, and we obtain minus Z sub F over Z sub I. And that should look familiar to you from a basic circuits class. Then if we plug in the particular parameters or expressions for those impedances, Z sub I was just R, Z sub F was the impedance of the capacitor, which is 1 over SC. We take their ratio, and that gives us the transfer function of that op-amp based circuit, and we, voila, get a scaled 1 over S with a negative sign, but we have a 1 over S, and a 1 over S in terms of an operation is an integration operation. There's our integrator, if we want it, from a fairly basic circuit. We have this op-amp circuit, you can now go, now, might not want to do this, but ideally you could build this with an R and a C. The gain now is going to be 1 over RC, but the main operation is this 1 over S. You're now having an integrator, which in the time domain, you inject some input signal, V sub I of tau, and you're integrating that with a weighting of minus 1 over RC. Now if you see this all integrator block diagram and you go, I have no idea how this would work or how we would do this, you can fall back on this piece of today's class and say, I know how to build an integrator, or I know what that really means, or I know what that is. So I don't have to really stress too much about what's an all integrator block diagram. It's just integrators with some gains and summing junctions all interconnected to essentially solve coupled differential equations. That's filling in some gaps maybe from the last time we were together. Now let's complete what we, I think, really finished last time, but I will go ahead and put some numbers in. But now let's go through this very quickly in continuous time setting, going from a state space representation into a transfer function, where now we are talking about generically having a system matrix A, which its dimensions depend on how many state variables we have, and each of those state variables will be in the vector x. What's maybe not so clear is right here. That integrator is more than just one integrator. That's a bank of integrators depending on the dimension of your system, where the dimension of the system is determined by the state vector. There's x prime, and right here would be x of t. This is now a bank of n integrators. So instead of drawing all of these n integrators interconnected in a weird way, we can collapse all of that mess down into a very, let's say, condensed form, where we now have all of the interconnection is in the A matrix, and we also have how the input is injected into all of those first order derivatives of our state vector through the input matrix B. We have a direct feed through matrix D, which in our particular example from last time was 0, and our output matrix C tells us how we linearly combine the state vector components, x sub 1, x sub 2, etc., to form the output Y. If you now wanted something to do, which I'm sure you do tonight, you can now verify these matrix expressions. The A matrix, the B matrix, and the C matrix from last time's or last lecture's RC circuit. We had a couple of resistors, we had a couple of capacitors. They were interconnected in a certain way. If we assume these values for the R's and these values for the C's, then you should be able to find numerical values for the system matrix A. And now these are nice and clean. I've picked some very generic values for R's and C's, but our system matrix A now is 2 by 2, and it has a -3, 1, 2, -2 as its 4 element values. The B matrix, if you remember from last time, it just had a non-zero value in the top entry, and in this case, for those choices of R's and C's, that particular value is a 2. And our output matrix, we were just measuring the second state variable. C then is going to be 0, 1, and we had no direct feed through from the input to the output. That you should be able to verify, and I would encourage you to do that based on our block diagram or based on the circuit, but you should be able to convince yourself that this particular representation with those A, B, C, and D matrices are actually the ones that describe that second order RC circuit that we had last time. What we want to do, just to remind ourselves, is go from the time domain, which is this red circled expression, into a transfer function form. And we can do that, go from time domain to frequency domain by Laplace transforming. And because we're really interested in the transfer function, or the dynamics between the input and the output, not particular solutions, we can actually forget or neglect that vector of initial conditions. We'll just not even worry about that. So we neglect x at time t equals 0 minus, and in order to, let's say, combine the terms that contain the Laplace transform of the state vector, capital X of S, we need to go ahead and put in an identity matrix that's the same dimension as A. And I will be n by n. In our particular example, capital I is a 2 by 2 identity matrix, which means I have 1s on the diagonal and 0s elsewhere. That allows us now to write this dynamic relationship between our state components and the input in the frequency domain as this matrix operator Si minus A that scales capital X of S. We can solve that now for capital X of S by inverting or hitting on the left-hand side everything with Si minus A inverse. If we now Laplace transform the output equation, which is really almost trivial, we're simply capitalizing our variables, the y, x, and u, to take them from the time domain to the frequency domain. That's not what we're doing behind the scenes. We're actually Laplace transforming those waveforms, replacing capital X of S with this expression, and we now have a formula that interrelates the input, its Laplace transform, capital U of S, with the output's Laplace transform, Y of S. If we factor out the U of S, that's how we now obtain our G of S. G of S is now our cheer. So if somebody gives you an A matrix, a B matrix, a C matrix, and a D matrix, you can actually compute what results from those calculations and find G of S, which for our A, B, C, and D, you will end up with this G of S, or I did. You can check my work. Again, something else to do tonight is go home and find this transfer function G of S. One thing that should make you feel warm and fuzzy is what? Relative to that transfer function. Maybe there's a lot of things that make you feel warm and fuzzy, but the one that I'm thinking about now, what makes you feel warm and fuzzy about that transfer function G of S? And maybe some of you are saying nothing. That makes me break out into a cold sweat. But it should make you feel maybe a little bit less stressed. What seems consistent with that transfer function and the circuit that we had last time when we were together? Anything? Well, I've succeeded in putting this entire classroom to sleep. I hope I haven't done that if you're listening to this at home. No one, well, maybe you're feeling so warm and fuzzy you just fell asleep. Is that, so now I guess if you're at home, you're cuddled up with your teddy bear or your cat or your dog or something to make you feel comfortable. But what in that G of S makes you feel comfortable relative to the circuit that we sketched last time? Anything? Yes. The fact that there are two poles. Why are there two poles? We had an S squared, don't we, in that denominator, and that should make us feel somewhat reassured because we had two energy storage devices. We had two capacitors. And it was an RC circuit. Another thing to make you feel warm and fuzzy is, where are those poles located? In the left half plane, or they have negative real parts, S equal to -1 and S equal to -5. Those are stable. We had a passive RC circuit which shouldn't be unstable. If we excite it with a bounded input, we should get a bounded output signal everywhere in our circuit. There's a couple of things that should make us feel warm and fuzzy. What's the DC gain of that transfer function? If I plug in a frequency of S equal to 0, I get 4/4, or a DC gain of 1. So now, if I inject a constant input to that voltage source in this RC circuit, I should see that voltage source at the output. If I plugged in 2.5, I better measure 2.5 volts across that output capacitor. Those are some things to sort of think about or examine, and you could do that with your circuit, right? You could look at it in the limit. As time goes to infinity, what happens to capacitors when you have a DC excitation? Do they short? Do they open? What do capacitors do in the steady state? Oh my gosh, really? I have to remember 320? Or that's a prerequisite for this class, so we might as well bring it back. Those capacitors open, correct? So now you could analyze that circuit under steady state conditions, DC, and see if you get a DC gain of 1. Question?
Might be wrong, but is that a factor S+1, S+4?
Hup! I'm just seeing, I thought maybe you guys were still asleep. Thank you. Somebody was actually awake. I wasn't when I was writing this. Actually, I knew I was thinking of 5, obviously, because 1 plus 4 is 5, but 1 times 4 is 4, which I need in that product of S+1, S+4. It's still stable, isn't it? But thank you. No wonder you guys didn't want to mention anything or speak up. You're going, I don't know how you got that. Answer. Now are we better? Now do we feel a little bit more comfortable with that result? Now you can check that and see what happens when you get home. So let's now move into the stuff that we will slow down on and work through today. Let's talk about a discrete time system, or a student loan repayment. Maybe this is being optimistic that the loan is only $10,000, but bear with me, okay? Let's be optimistic. Suppose that we now have a student loan, and we're going to now try to use that example to derive a linear difference equation. And then you'll be able to apply this to other investment scenarios if you so desire. And your engineers, you're going to be wanting to invest, right? With all of your hard-earned earnings. So let's assume that we have a principal of $10,000, and let's just assume that we have an interest of 5%. I'm trying to get some nice numbers. And a time horizon of 10 years. That's now the the given information, we want to now put that into a difference equation, a discrete time difference equation, and maybe create a block diagram. Now you can go into your financial advisor and say, here's the block diagram of my investment portfolio, and he's going to look at, he's probably going to fall asleep, right? Or run out of the room and saying, who am I working with here? But you'll be way ahead of most of his other clients or her clients. So now let's figure out how to turn this into a linear difference equation. We have a principal of $10,000, an interest of 5%. That's how much we're being charged. And we want, with this time horizon, we want to have this loan paid off at the end of 10 years. That's the objective. Can we now sketch? I'm all for sketching. Can we draw a picture of that scenario? And in particular, what does 10,000 represent? Well, let's just say that that is now our initial, let's say, balance in this formulation of a linear difference equation. So I'm going to say that this is now the initial balance, and we can call that P sub 0. So that's the principal at time 0. And this R is actually the annual interest in percent. So we'll have to convert that to 0.05 if we want to use it. And now let's go ahead and so this P sub 0 is based on our notation. We'll let that be P sub 0. And what do we want? This is now $10,000. And if we did nothing, it would just stay there, right? If we didn't have any interest, if we didn't have any payment to worry about, we would just continue with P sub 0 being due at 10,000. But what are we wanting to have happen? We want, at the end of 10 years, we want to have a balance of 0, so in effect, we want P sub 10 to be 0. And between P sub 0 and P sub 10, we need to figure out what that looks like. If we didn't make a payment, what would be the principal after 1 year? If we didn't make a payment, at the end of 1 year, what's our balance? It's the initial plus the interest. So now we're not only at 10,000, but now we've gone up because of the interest, P sub 0 times R. And what we're trying to do is figure out, can we now knock that down by some payment, let's say U, so that maybe we get to P sub 1 at the end of 1 year. And we are now looking to figure out, how do we find U? We want that to be the same. We want U to be fixed. P sub 2, hopefully if we pick the right U, it will start being less than P sub 1, etc. Does that picture look okay? Now let's see if we can put some equations behind or that describe that particular picture. R is our interest. annual interest, and P1 is the balance after 1 year. And U that I'm using is the yearly payment, and we're making that at the end of each year. And our main question now is, what are these values? What will U be, or what are the yearly payments? What's an expression in terms of all these P's and U's and R's that we can write down that should be describing what we've tried to indicate P sub 1 is equal to in terms of P sub 0, R, and U? Can you see an equation just based on this picture? What P sub 1 is equal to? What's this dot there? Did you see me make the dot? So P1 is the original balance plus the interest, which is the balance at the beginning of that year times the interest rate R, P sub 0 times R. And now we want to subtract the payment. So P1 should be P0 plus P0R minus U. Are we comfortable with that? And we can write this a little bit more compactly. We can say 1 plus R P sub 0 P1 minus U. That's after 1 year. After 2 years, can you write or find an equation for P sub 2 based on P1 and U? It's now P1 plus P1 times R minus U. Same structure that we just had. And if we combine that as we did before, we have 1 plus R times P1 minus U. That's P sub 2. And I think you see the pattern. Now the general equation is now P at n plus 1 is 1 plus R P sub n minus U, and that's true for n equal to 0, 2, on up to n. Now, do you see a block diagram? Now that we have a general equation, we have something at time step n plus 1 equaling something at the time step before and an input, which we're taking away from that other piece of our equation. Meaning, if I now said, well, let's see if we can find a block diagram that might actually be consistent with that first order difference equation, this will now be an all delay block diagram. So I'll just call it a BD. We'll use some abbreviations occasionally. Now let's say that I have a unit delay. In this case, the unit is 1 year. And if I now inject into that, or put as an input into that unit delay, if I put p sub n plus 1, if I put p sub n plus 1 into a drawer and then I open that drawer 1 year later, what's going to pop out? Or if I now had p of 10, and how is that if you delay it by a year, or what was that 1 year before? That's really what we're saying is the output. So this should be p of what? P sub n. So now if we had something, p at 8, if we waited a full year, then that value would actually be, how do I want to say that? The input to that delay block would then be p of 9, and coming out would be p of 8. Now how do we interconnect that to make this equation true? We have p of n plus 1, we have p of n. We simply need to combine two terms to make p of n plus 1. One of the terms is easy. We simply need to subtract u to make p of n plus 1, and the other one is a scaled version of p of n, p sub n. And that is now an all delay block diagram that's consistent with that first order difference equation. And I have one delay block, which gives me the 1, or the first order difference equation. What we want to do is actually find this yearly payment little u. How much do we need to subtract off each year so that after 10 years p sub 10 is now 0? We know that's true, but we also have an equation for P1 in terms of P sub 0. Or we could now write this as 1 plus r times our P1 expression in terms of P sub 0, so that we're relating future values of P to the initial balance, or P sub 0. This was now 1 plus r times P sub 0 minus u minus u. This is just P sub 1. Or I now have 1 plus r squared times P sub 0 minus 1 plus r u minus u. And if you wanted to make the pattern look a little bit cleaner, you could write that 1, that coefficient of 1, as 1 plus r to the 0. So that now we have minus 1 plus r to the 0 times u, and we have another term, 1 plus r to the 1 times u, and we have a square term or factor scaling P sub 0. If that structure holds true for P sub 2, can you tell me what P sub 3 looks like? There is now our expression for P sub 3. And if we continued with that, we could say in general, if I now wanted P sub n, I would have 1 plus r to the n times P sub 0 minus, And now we need to put in some maybe simplifying notation. We could put in a summation. We could sum from L equals 0 up to 1 less than capital N of 1 plus R to the L times U. And maybe we can make it a little bit cleaner and say, let's just factor that U out of that ugly summation operation. And this formula, you should be able to go back and plug in P sub 2, P sub 3, P sub 4, and see that you get exactly the same expression that we had before. And what do we know in this expression? We're trying to find U, aren't we? We know R, we know capital N. Capital N is 10. What we would like to find is that. If we could find that, a number for S, we could solve for U. U would be our only unknown in that expression. But we know capital N, we know R, so we should maybe be able to, we could sit down with a paper and pencil and add that up, right? We just have 9 terms to add up, but we can be a little bit more clever and find it maybe more algebraically. So let's do that. Suppose that I said, well, S, and now notice that I'm leaving some space. Okay, hint, hint. So I'm going to write something in that space, but now I'm going to write something here. Suppose that I say S. That's that mess. And what is that? Well, when L is equal to 0, it's just 1. When L is equal to 1, it's 1 plus R. 1 plus R squared, and it just keeps going up to 1 plus R to the power capital N minus 1. And you could sit there and add that up, correct? You could figure out what that sum equals. But we can be a little bit more creative and say, well, if that's what S equals, I can also say that 1 plus R times S is equal to what? Now I just hit all of those terms by 1 plus R. And the 1 now becomes 1 plus R, and let me write that here. Then the 1 plus R times 1 plus R is just 1 plus R squared. Now I have to widen my paper, and I can do that. I have an infinitely wide piece of paper. And now I have one more term, don't I? 1 plus R to the N. Everybody okay with what I've done? And now I can compare those, or I can subtract those. I can now take this bottom expression and subtract it from the top expression. And up here, on the left-hand side, I really just have S plus R times S equaling what's on the right-hand side. And this term gets canceled by that, this term by that, etc., all the way up to here. And what do I have left when I compare those, or when I subtract the bottom from the top? That algebra agreeable? Hopefully I didn't convert a 5 or a 4 into a 5. I have a way of doing that, so make sure and keep me honest, especially with low blood sugar at this time of day, huh? If I faint, I guess you're all just released. You can just leave me, and the next person that comes in at 7 in the morning or whenever, maybe the janitor would roust me at 2 a.m. or something, whenever they come to clean this place up. Where am I? Oh, with low blood sugar, trying to figure out this formula. Now do we have an expression for S? We can now solve this for S by just dividing everything by little r. And I can say, oh, that's 1 plus r to the n minus 1 over r. And there is a closed form expression for S, this summation, this finite sum that I can use if I know capital N and I know R. And for our particular problem, little r was 5% or 0.05, and n was equal to 10. Or S now becomes 1 plus 0.05 raised to the 10th minus 1 over 0.05, and this, if you calculate it out, ends up being 1.62889 with a few significant figures. And this is, well, 5 over 100, which is 1 over 20. So now this is going to be 20 times 1.62889 minus 1, or 0.62889. So having a period of 10 years with a interest of 5% says, oh, you're basically going to be multiplying or scaling by 20 times 0.6, or 62% of 20, which is a little bit more than 12, for S, which is 12.58. That's now S. We can now plug that into P sub n equaling 1 plus r to the n times P sub 0 minus SU. S we just computed to be 12.58, and this was 10.05. This was 10,000. What's P sub capital N, or this was 10? And what did we want that to be? 0. Now the only unknown in this is U, so if we solve for U, we end up, this is back to what we had before, 1.62889. This ends up being $1,295.05. That's now our annual payment. And does that make sense? Or does that seem reasonable? What if we didn't have any interest? What if R was 0? What would our annual payment be if we needed to pay off $10,000 in 10 years? $1,000. And so we would expect it to be a little bit more than $1,000. So it seems like it's reasonable. Is that going to be doable? Well, if you said you're making $70,000 right out of the gate as an ECE major, maybe that's lower than what you'll be making. I don't know, but that now ends up being 0.185, or about 2% of your annual pay that you're going to be paying off your student loan in 10 years with. One way to think about it. In terms of reasonableness. Questions on that? Example. Or a visit with reality. Oh, I have more than 10,000. My interest is different, but now you know how to figure that or determine that. What if you were putting pennies into your piggy bank before you started college, or maybe not when you were really young, but what if we actually saved $1,000 per year at an interest rate of 2%, which you might be able to make now, maybe, with a fairly safe investment. What's this look like? What kind of a difference equation does this look like? Or what kind of a timeline do you see happening here? What's p sub 0? Now let's assume that we begin at the beginning. P sub 0 is our initial deposit of $1,000. So let's now say that, and now what's P1, P2, etc. P sub 0, let's say that's now U bar, that's our $1,000. What's P1? We continue to deposit $1,000 every year. Or this now, and let me call that R bar since it's not the same R as we had before. Now we have 1 plus R bar, P sub 0, plus U bar. What's P sub 2? In terms of P sub 1. Pretty easy, these linear difference equations, aren't they? And if you just kept going, you could just start doing this. If you were feeling warm and fuzzy tonight, you could say, oh, P sub 8. You could just add these up and find that at 8 years you now have accumulated $9,754 instead of $9,000. And can you now draw the block diagram? Do you see what kind of questions I'm going to ask on the final? I have an investment scenario with the following. Who knows? But you can now draw a block diagram. You can get partial credit by putting this in there, right? A unit delay. You can say, oh, here's a block diagram, an all delay block diagram, but what are we doing now? Now we have P sub n plus 1. You know coming out of that is P sub n. And what creates the output of that summing junction? Our annual payment of U bar, and now it has a positive sign. And we scale that by 1 plus r bar, the previous value of our balance, p sub n. And if we now look at p sub 9, and the moral of that story is plan ahead. Did you start saving for college when you were in diapers? Maybe you would have part of your tuition paid for the first week of class if you had. All joking aside, now you can see that you can create linear difference equations without too much effort and maybe answer or think about some interesting scenarios. This is a first order system. In this case, is that system stable or unstable in this block diagram? I'm putting in a bounded input of 1,000. What's coming out? If I just keep putting in that 1,000, keep putting in that 1,000, what's going to come out? Is it going to remain bounded? For large values of time, that's just continuing to grow, isn't it? So this is actually an unstable system. And you can see that the system matrix, or the A matrix in this case that we will talk about for the discrete time system, now has a pole bigger than 1. It's at 1.02 in this example. And stability in the discrete time case is all based on not the left half plane, but the unit circle in the complex z-plane. And we want our poles inside the unit circle if we wanted our system to be stable. Poles outside the unit circle, they can be real, they can be complex, but those poles that have a magnitude bigger than 1 correspond to unstable systems. In your bank account, you want it to be unstable, right? You want it to grow unbounded with time. So that's a good thing here for an unstable system. That being said, let's move then to the next sort of round, which is in more general sense. Let's look at homogeneous difference equations. And I may be a little bit lax. We'll probably always have linear, but I've failed to include that adjective. But homogeneous linear difference equations. And to give us something to chew on as we're looking at this, let's just think of the following. Suppose that I now have x of n plus 3x at time n minus 1 plus 2 x at time n minus 2 equaling 0. And this homogeneous really just means we have no external input, or there's no u of n term that's driving this difference or this dynamic relationship on our variable of interest, x at time n. And let's now just assume some initial conditions. Suppose that we say our initial conditions suppose we have x one time step before 0, or x at minus 1 is 0, and x right at 0, let's say that's equal to 1. And now what I want to do is find a closed form expression for x of n. You could iteratively evaluate for x at any time period little n. You could just solve this equation for x of n and start substituting in the values for x of minus 2, x of minus 1, and moving forward to find x of 1, x of 2, etc., iteratively. But we want to find a closed form expression for x of n so that I might say, what's x going to equal at time step 27? And on the final exam, you may not have time to iterate up to 27, or I might even say 1062 is your time step in. Just so if you're doing that on the final, well, good luck. You want to find the closed form expression. So let's now find a closed form solution. And to do that, we're going to treat this similarly to maybe how you treated differential equations in a differential equations class. What we're going to do is we're going to assume a structure for the solution. Assume a solution form that looks like x of n is now some constant a, z to the n. And don't confuse that with the A matrix, the system matrix. It's just some variable a, and z is a complex number, and we're raising that to the nth power for x at time step n, where a and z are really the values that we're trying to find, are values that need to be determined. And if you are thinking back a year or two or whenever you took your differential equation class, you could actually compare that a e to the st for some form of a solution for a continuous time solution if you were solving linear difference equations. Linear differential equations. Again, that blood sugar is going to... You've measured it by my inaccuracies in my speech, right? Indirectly. Okay, so now we have this assumed solution form. If we plug that back into this equation, what we're trying to find is a way to find a and z, values for a and z. If we plug this structure into that equation, we will end up with x of n, which we said was a z to the n. That's just x at little n. Then it was plus 3x of n minus 1, and what does that look like with this assumed solution form? What's 3x at time n minus 1 look like? If this is x of n, what's x of n minus 1? A times z raised to the n minus 1, and we need to scale it by 3, so now we have 3a z to the n minus 1. And finally, it was 2x of n minus 2. I hope that's what it was, so that this now becomes 2a z to the n minus 2 equals 0. Again, we're trying to find a way to find z's or a's. Well, if we want a non-trivial solution, those two constants need to be non-zero. A needs to be non-zero and z needs to be non-zero. What if we factored out from that equation az to the n minus 2? If I factor that out of all three of those terms to the left of that equality sign, what do I have when I have az to the n minus 2 times something to give me az to the n? What does that something need to be? It just needs to be z squared. The next one, three z plus 2, and all of that needs to be equal to 0. And I said for a non-trivial solution, I need that to be equal to not equal to 0, so I can divide that out, and that now forces this polynomial to equal 0. And this is the characteristic polynomial associated with that linear difference equation that we started with. And if I set that equal to 0, then setting the characteristic polynomial equal to 0 will give us our characteristic equation. And we can now use that to find values of z that make that characteristic equation true. Or what values of z cause the characteristic polynomial to equal 0. And now I need your help because of low blood sugar, right? I couldn't even get 4 and 5 to work, but this one should be fairly straightforward. So it's z plus 1 times z plus 3, right? Doesn't take much to humor this old man, huh? So there we go. Z plus 1 times z plus 2. Is that right? So what values of z solve the characteristic equation? If I plugged in z equal to minus 1, that would force it to equal 0. Or z equal to minus 2 will cause it to equal 0. And now I have my modes of my solution. I have two modes. One is at minus 1 and one is at minus 2. And that actually gives me my generic solution structure for this linear difference equation. X of n is now a1 times minus 1 to the n plus a sub 2 minus 2 to the n. And this is not quite the solution, but if I just ask on the final, what's the closed form structure, you would just have to find the values of z that satisfy your characteristic equation. And you wouldn't have to solve for the a1 and the a2 and the a3 and the a4, depending on the order of that difference equation. Here it was second order, and I have now two modes. So now how do I find my a's, my a1 and a2? What have I not used so far in this discussion? My initial conditions. Now I can solve for the a1 and the a2 using the initial conditions. So I can now find a1 and a2 from the initial conditions. X of 0 I said was 1. If I plug that into this structure, I then have a1 times 1, or minus 1 to the 0, plus a sub 2 times minus 2 to the 0, or a sub 2 times 1, or I now have 1 is equal to a1 plus a2. Or for this second order difference equation, I need two initial conditions to try to solve for my unknown coefficients. Here's one equation, but I also said that x at time minus 1 was equal to 0. I can now plug in little n equal to minus 1. Or I now have minus a1 minus 1/2 a2, or a1 is minus 1/2 of a2. And if I use that in my previous relationship for a1 and a2, 1 was equal to the sum of a1, which is minus 1/2 a2 plus a2. Summing those up, I now have that a2 is equal to 2, and a1 is the negative of half of that, or a1 is minus 1. And now I have my closed form solution. My closed form solution is now a1 minus 1 times minus 1 to the n plus a sub 2, which was 2, times minus 2 to the n, and this is true for n greater than or equal to 0, and you could plug in n of some large value without having to iteratively solve for x at each intermediate value. This is now our closed form solution. What does x look like as a function of time? And can you anticipate what it's going to look like based on what we've talked about before? Well, we know that x at minus 1, so if you couldn't even solve it, you could at least put that down, right? You could say, oh, the behavior of x of n. Oh, I ran out of time. But x of minus 1 was 0, and x of 1 was 1. Those I gave you. Those were the initial conditions. What's x at time 2? What am I doing? Converting 1 to 0 now. X of 0 was 1. That better? Maybe. What's x at time 1? Well, I could plug it into the closed form, or I could actually iterate, but in this case it's minus 1 times minus 1 to the 1 plus 2 times minus 2 to the 1, or 1 minus 4 equal minus 3. What's x at time 2? Seven. What's x of 3? Would you like to be writing on the head of that x stem? If you viewed it as a stem plot, I started at 1, then I went to minus 3, then I went to 7, then I went to minus 15. Is that making any sense, or is it consistent with what you would have expected? Where were our modes? What were the values of z that solved that characteristic equation. -1 and -2. Where were they relative to the unit circle? If I took the absolute value of those, or the magnitudes of those, where were they? 1 was right on the stability boundary at 1, and 1 was way outside at 2. So your solution is growing, but with a negative value, it's oscillating back and forth. It's going positive, negative, and it's growing as it's doing that, and that's what this is telling us. So now we've iteratively figured out, using the solution, that we have an unstable system, and we could have immediately said that by just looking at the characteristic, or the solutions to the characteristic equation. We'll pick up next time with non-homogeneous or forced linear difference equations when we meet again.